So I think it's really important you know about the process you're going to model. You've got to know how it works to some extent, because you can't apply your mathematics until you know how it works. Because the mathematics sits there in isolation, unrelated to anything until you start drawing links to it.
Today I have the pleasure of interviewing David Fletcher of Leap Australia. Thanks to Leap for sponsoring this episode. David has over 40 years of CFD experience. He has published over 340 journal papers in CFD with an emphasis in combustion, multi-phase flow, mixing, and biomedical systems. He's also an adjunct professor at the Sydney University. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. Thank you for joining today, David. It's so good to have you on the show.
It's a real pleasure. Yeah, I love talking about CFD, so it's actually my pleasure.
Well, that's fantastic. So we'll jump right to it. You've mentioned that you wrote your own streamline vorticity code to study mass transfer during your PhD, and a lot of students, right, as the CFD field has changed, a lot of students don't have that experience of writing their own code. They're maybe using a commercial code or modifying an existing in-house code at the university. But what experience did that teach you, writing your own code from scratch during your PhD?
Well, back in that time, computing resources were very scarce and you were writing to punch cards. So one of the key things was to be careful, to do a lot of planning. So whenever I wrote some code, I actually sat down and thought about what it was going to be, wrote it, and checked very carefully. You couldn't afford to just dash something off and give it a try, because that might be 24 hours before you saw the results of that. And when it came back and you'd spelt continue wrong and hadn't checked it, you had nothing for the day. So I think that's one thing, care. The other thing it made you really aware of is what assumptions you have to make. So streamline, vorticity, it's good for some things, but there are quite a few places in a flow where it's poorly defined, like at a step. And you have to make an assumption and change the actual equations at that point to get a solution. So it also makes you realize that there's lots of tips and tricks in a code. You know, even when the equations are written out, that is not the full story. To make it work, there's lots of inside things you have to play with at special locations, and do special practices to make it stable. And I guess these are the tips and tricks that get embedded in commercial software, for example, but are not in the manual. So anybody could write out the Navier-Stokes, but can you program them stably for a typical geometry? That's a whole other game. And I guess the final thing I took away from that is that streamlines have a very special meaning. They come from a stream function, and even pretty well every commercial software is wrong. They talk about streamlines when they're actually calculating streaklines. They're not actual streamlines. They don't come from a stream function. And constantly correcting that, both in papers I review and explaining it to people who will draw streamlines through a transient flow, it's just wrong. But if you haven't had those experiences of the rigor of doing things yourself, you just don't know.
Yeah. So for the benefit of some new listeners, right? We have a lot of people that listen to the show. Can you clearly define the distinction for them for Streaklines and Streamlines to maybe wipe up any muddled ideas?
So a streamline is coming from, usually you calculate it by having a defined stream function, and that's a line that's everywhere tangent to the flow field. Streaklines are what you get if you drop a particle into a flow, or a tiny, tiny blob of ink, but no diffusion, and you follow that around. So that is just following a pathway. And In some circumstances, that gives you the same as a streamline, but in others, it does not. And in particularly, if you think about a transient flow and you've got a particular set of data sitting there, you can't trace the flow from that alone. You need to see particles at the inlet over time and follow their position, and that will give you the closest you can get to a streamline, even though in transient flows like that, it's not actually rigorously defined. So
Yeah.
you have to be super careful what to interpret. And this is the origin of the dilemma people have when, say, they're modeling a fan and they draw streak lines and they go straight through the fan. It's because they're solving streak lines and they're that instantaneous flow. But if they actually solve them in transient mode, they'll actually see them follow around, pass around the blades and back out again, and there will be no flow through a solid wall. So it's quite important in post-processing to have that clear in your mind.
Yeah. Yeah. Thank you. Thank you for expounding on that. So it looks like there were a lot of things that you got in your experience writing your own code
Mm,
and moving forward. And so you've had the opportunity throughout your career to mention over 100 graduate students.
mm,
And how have you taken what you've learned and how has that shaped your approach to teaching and
mm,
mentoring, right? And I talked about this with you just a little bit before the show, but you have one of these unique roles that I find particularly unique of having involvement with the university on an advising level and teaching level, but then also very involved in industry
mm,
and working in the industry as a consultancy
mm,
partner with ANSYS through LEAP. And so how has that shaped your mentoring that you provide to your students?
mm. That's a good question. Uh, I think one thing that's very noticeable, um, and particularly if I'm in a room with a group of people, because I did mathematics as my background, my first
Mm,
thought is equations.
okay.
And when I was first at the university here, I taught a course in transport phenomena, which is very classical in chemical engineering. And I also did that in a parallel role with some CFD. So we
Okay.
would look at different flow fields, compute them, go and look at the equations. Now, I guess it must be around 2000, the year 2000 now, that course got dropped because interest in it reduced. So even though the software was getting better and we could do more, interest reduced because there's this falling off of interest in knowing anything about equations. And it's a big trend here in Australia. I know it's not a big trend in the really good European US universities, but here engineers don't really want to do mathematics. So to accommodate that, you have to try and explain things without doing mathematics, which is hard, I think. Very hard to explain a lot of concept rigorously. I also noticed in parallel with this, I did a lot of training with the commercial software. And there was a really solid 4-day course when people bought the software that they would do. And it would go through the equations, the setup, the models, the numerics. But there would be an awful lot of stop points in it where they had to go try something out. And they were on the spot, if you like, because I would be tutoring and they would have to do things. That's changed dramatically. I no longer teach those courses because they're now taught as like 5 2.5 hour grabs where they get a little bit of lecturing, they get a demo, and they're left with some exercises. But there's not that desire now to be on the spot and learn and ask questions. And
Mm,
I can distinctly remember when I used to teach as having some amazingly good asides on the blackboard and taking a pre-canned model and doing something to it to learn something and tailor it to maybe what people wanted to use. So there was there was much more engagement, in that learning process. I think the web and videos and that have made people want to grab stuff in small bursts, whereas they were much more willing to suffer, if you like, really do the hard yard and put their hand up and say, really, I don't understand this. And you would actually find a lot of other people didn't, and they were grateful to know. And you could
Yeah.
actually, thresh out the problems with them, and people would go away much richer in experience of what they've learned. And so now I really notice that even when you have PhD students, that there are a few that are still interested in the mathematics, but they're the minority. But most feel under pressure to just get results. Um, but I'm still trying to maintain that rigor of checking what they do. So
Yeah.
they know not to come to my office with questions unless they've brought a file, so that we can actually look at what they're doing and it's not some vague, thing. And then during that process, we'll go back to the beginning and look through the setup.
Yeah.
And I'm super keen on that level of one-on-one mentoring. So
Mhm.
that's a real feature of how I teach on my PhD students.
Yeah. That's very, very similar to what I've read about Brian Spalding's at Imperial College methodology. He said, any of my students are welcome to meet with me anytime, but first, I need a written description of the problem,
Mm,
what you've tried, and what hasn't worked or what you're still struggling with. And
mm,
one of his students had said, by that point, we almost always figured it out ourselves,
yeah.
of going through those steps, but very, very, very insightful
Mm,
on that. So how has your approach then evolved over time? Because what I notice is in doing these interviews with people who had the opportunity and the experience of learning, um, when things weren't so connected,
mm,
right? It wasn't so easy to find something on the web or
mm,
to just get a quick answer, that there was a different mindset
mm,
almost in the way that we worked, right? And this isn't unique to
mm,
CFD. This
mm,
is this is global. It
yeah,
changes with the internet, right? And the
right.
web and how things have changed, social media, there's instant access. So how has your approach evolved over time in that mentoring? Do you find that you have to just recalibrate expectations with students of the math still matters and this is um
Mm,
yeah, that it's almost just because other things are quick doesn't mean math suddenly got quick and
mm.
easy, right?
So I think you do have to recalibrate and be willing, um, not to push it so much, but also you have to realize when you've got a really good student that
Mm,
pushing it a little bit will get them interested. And although they probably don't like to admit they've got interested in it, they actually do get interested in it and want to know more. Um,
yeah,
and certainly, you know, that this whole question of when do you stop checking your work is a big one for them. Um, some of my students have published very little by the time they submit their PhD, because we've been checking up until the day they submit and then they publish after. Others have got papers out within 3 months almost, where they've just dashed something off. Um, but I'd be in tears if my name was on it, when you see what they're publishing.
yeah,
So you've got to take every individual differently, but the
yeah,
ones that you feel have got a good career ahead of them in CFD, you have to keep seeding them with the mathematics in the hope that they really take it on board.
yeah,
Because I think, to me, that's the big differentiator. Somebody who can write down some equations and draw some conclusions based on equation type. Um,
yeah,
I've had these occasions where, like, somebody's doing a problem with say conduction, and you look at their results and you say it's wrong, and they're like, but you haven't looked. And you say, well, yeah, I don't need to look because your temperature is massive, beyond the boundary conditions when you've got no source term. So mathematics tells me this is wrong without having to bother to even look at your residuals or your balances or anything. Yeah.
Yeah. Yeah.
Um,
That's that's a great example.
mm,
Great example. Yeah. So just anecdote here. That's exactly how I started,
mm,
was not thinking that the equations were as important as they are. And I'm
mm,
grateful every time I voiced that. I had mentors that politely but firmly said,
mm,
Cade, you're off base. The
mm.
equations are what matter.
Yeah.
And that's how we're representing and getting it. And so that pushed me down a path, and I resisted at first. But once I did finally see the light, I willingly signed up for the hard yard, and it's paid
Mm,
off. I don't
mm.
regret that
Yeah.
at all. So that I can relate, and for anyone who's listening, I can second what David has said there on the student side of it. Um, so in this, I guess, put context for the rest of this conversation. You wrote a paper for I can't remember what journal it was published. Was it the
Chemical
chemical?
engineering research and design. It was for their
Okay.
100th anniversary invitation. They asked for a group of perspective papers,
Hmm.
and I was asked by the fluids editor to write something on CFD.
Yeah, and I'll put a link to the article in the show notes. But when I came across that article, I had two thoughts. One was I want to get David on the show, and two was this is just phenomenal. And one of the things that you talk about in that, you go through some, I believe it's 10 lessons that
Mm,
you'd highlighted throughout your career. And one of those that you mention is that a strong interaction between simulation experts and operating staff is better than trying to make all staff part-time simulation engineers.
mm,
And I've personally experienced a few different organizations where you've got this relationship between the analysis team and maybe the operations team
mm,
or the design team, whatever
mm,
team it is. But that integration has been less tight in
mm,
some organizations, and it's been very tight in others. But
mm,
I wanted to ask you for your insight on, can you provide some examples that have really worked well of how someone might go about improving that collaboration between
mm,
those two? Because I think for some reason it feels like, and we even have this within CFD, right? And it's
mm,
less so now, hopefully, but experimentalists versus computational engineers,
mm,
right? That we're all trying to help each other
mm,
get to a better design or a better product or something,
mm.
but it feels like there's some conflict unnecessarily.
Yeah. So I mean, the first point there, I think, is that neither can survive on their own. So a CFD, a good CFT team, is not going to put a design team out of business or an experimental team. What they're going to do is focus them to do better experiment or to try more useful designs. And so there should be no competition. There should be two-way communication, which is super important. There should be confidence in each other. And that is super important too, that
Yeah.
the computational people know what the engineers on the plant are facing on a day-to-day and what pressures they're under, and the fact that they can't wait a year for a decision. They need quick decisions. They can't make use of a perfect solution because there's only a certain space they can put the pipe in. And so it's no good rushing in, making these really sweeping changes and going to them with the perfect duct and them saying, well, hang on, there's no way of getting that through the door into the plant. So there's that side of it. And then
Yeah.
there's the side of the CFD people need to earn the respect of the experimentalists and
Mm.
engineers. And by that, I mean, they need to show what they're doing. They need, often the good ones will have like a lunch and learn seminar where they show what they're doing. They must, must start off with something simple that people can understand and has a bit of an impact. So there's an important sort of message there make sure that you're able to communicate what benefits you're going to get from this, so that you can gain their confidence to wait a bit longer for a better solution. And also, in your ideal world, you want these engineers and that to come to the CFD team before they start a project, not when it's partway through and going wrong, and really engage at all stages. So the CFD people have to be, like follow the 80-20 rule. Don't go for perfection. Go for something that gives guidance now, and if warranted, make it better later. Now,
Yeah.
if you're interested, I could give a very specific company and person that I really respect who's done this.
Yeah.
Yeah.
Absolutely.
So the person is Dr. Gary Brown. The company is Alcoa. So Alcoa refine bauxite. And Gary was one of the first customers I brought on with CFX here when I was working with that. And he'd been given a year to prove his worth. So it was a nice example. He quickly picked up a small problem to do with erosion in blanked off pipe bends or
Okay.
T-bends. And, the fact that he showed the origin of that problem, and that really got people on side. And that team has grown to having more than a workstation, to be multiple people. And Gary wrote an article quite a while ago now, CFD from backstream curiosity to mainstream tool, or words of those effects. And he recently completed a PhD, who I was lucky enough to be like a co-supervisor of. And if you look what he did on day one when he joined the company, it is so basic compared to what he's just done in his PhD. But the impacts of both of them to the company have been super important. And what that says is, if you can build that relationship and that engagement, you can start applying simulation to so many things. And the good thing about the company there is they've allowed publication of stuff that's more generic. So it's allowed people like Gary and his team to present at conferences, to get critiqued by journals. And so they've got useful lessons from that, and stay super current. And that is the other thing. I think that they're one of these customers that are quick to try out the latest release of the software, because they don't want to get stuck in the 90s. They don't want to get stuck using slow or dated methods when they could do so much more with the current ones. So, a highly integrated group now within the company, doing all sorts of simulations. And there's a good few papers out there that we've done together over the years, showing what can be done for these industries. Now, like I said in the original thing, you'd say, well, why does a company actually publish this stuff? Well, they don't give away the commercial details. They validate on if you validate with a Rushton turbine, nobody knows what sort of impeller you're using still. And so it's really good to have that rigor, which impresses the people they're working with, who think, well, these guys know what they're doing. And so they're super active in supporting the plants. And it really is, it really comes down to having a very good team leader who's got the right attitude. And Gary has been a superb client, and more of a colleague than a client. And it's great to see the impact. So, if I contrast that with companies that invest just as much in the software and people, but they then they give it to somebody who they say, oh, you can, spend Friday afternoon knocking up some models. And they just don't get the value for money out of the software. They're actually better off not buying it, because they pay for the software, but they don't want to commit people to it. And so they never quite get to a solution. It's always the job is finished before they get there and they start the next one.
Mm-hmm.
And it's really not part of their performance assessment. It's much more important to get the testing done or whatever. So they
Yeah.
miss out on all this insight they would get from doing good CFD. And sometimes you're looking at the problem they're working on, thinking, my goodness, that is so ripe for simulation. If only, if only you guys at A kept up to date and B, had a good trained person working on it, you would be leaping ahead of your competition.
Yeah.
But
Yeah.
not to be. And I see that as a particularly kind of certainly Australian thing here, that the unwillingness to invest
Okay.
in personnel. They've bought the software, but they're not willing to invest in the personnel to do
Yeah.
it.
Yeah. It's not the return is not linear. If you invest this much
Mm,
in the software, you get this much return. It's it's not that way at all, right? You got
mm,
to be fully committed.
yeah.
So,
And
yeah.
when you see committed groups doing it, you see what a massive, massive impact they have on the business, to
Yeah.
the point where the business can't conceive of not having a simulation team, right?
No.
It's not just equal. It's like we cannot function without the simulation team.
Mm.
Mm,
And that's we started. I find this very very striking how quickly we get to this subject of doing CFD and providing value. Right. We started with the mathematics and how
mm,
one of the keys is you've got to know the mathematics. You
mm,
can't gloss over that.
mm,
But it's also surprising how quickly we get to some of these other I'll call them dimensions of
mm,
CFD that are required to provide value. You've got to be
mm,
able to articulate. You've got to be able to understand what drives business value for the
mm,
company. Because in some teams I've worked on, I've asked my supervisor, what are your number one goals? And they haven't been able to give me an
mm,
answer. And so it
mm.
makes it very
Yeah.
difficult of how do you make CFD win if you don't know
Mm,
what winning means
yeah.
for the company or the
Agreed.
team? So yeah, I think that's these are things that often are not talked about in
Mm,
school, and if they are, and not that they have to be, right? I'm not saying
mm,
all of this has to come from school, but they're things that if you want to be successful,
mm.
you need to figure out how to learn and how to deploy this, and get
Yeah.
the people who are committing financial resources to be invested.
I agreed. It's so important to have that probably management um person who sees the value and sees that committing resources to this is going to change their bottom line. And that
Hmm.
bottom line can be super simple. It could just be saving a period of maintenance, you
Hmm.
know, and so you're
Yeah.
producing 24/7, you reduce maintenance, or you have fewer prototypes, or you solve some problem that's been bothering your mixer or or your electric iron or whatever, and get your place back in the market.
Yeah.
It's so important to have that confidence in the engineers doing simulation, to let them
Yeah.
run with it and to support them and give them the time to run with it.
Hmm. Yeah, I find it striking too that you said they gave him a year. I think um, when you were talking about Gary, right?
Mm,
They hired
yeah,
him and gave him a year to kind of prove his financial uh, viability per se. Um, but these things do take a long time. Like
yeah,
when you talk about um, simulation in a company and company timelines are there's a lot that goes on. And so for anyone
mm,
listening, I think that that's important to recognize
mm,
what you're signing up for
mm,
is a long haul
mm,
investment that companies who are doing it, they're not committing less resources to simulation. The ones who figured it out, right? They're figuring out how
yeah,
can we get more value and more value from
absolutely,
simulation. So
absolutely.
yeah.
And those are the companies that work very closely with the vendors and that to take on board new technologies, new ideas, and not be frightened to say, okay, what I'm doing now is outdated since, the last release. I'm willing to
Hmm.
try the new measure because it's going to be 5 times faster and better quality. I'm not
Yeah.
fixed in my old way. And then you've got the
Yeah.
others. I mean, there are still people who insist that you can only work with structured meshes. Now, you know, and some of these come from old time academics who have not kept current. And you see the
Mm.
most appalling structured meshes that Eddie's polyhex core mesh would leave for dead. And the poor students have struggled with isom hexa for weeks to get. And the first thing I tell them when I'm on support looking at something like that, this mesh is doomed. You can't ever get a solution on this. It's way too poor quality. Just hex core mesh it. And when they see you do it for them in 2 minutes, they're like, oh my gosh. And that's one of the examples of, if you don't keep up with the modern technology, you cannot keep up with the provision of services and models and that in an industrial setting.
Yeah. It's moving so quickly now
Mm.
that you don't have time. Yeah, it's going fast. So one comment that I've wondered your take on is I have some uh, contacts and people that often recommended to me. I don't follow the most recent release because there's too many bugs in it, so I stay
Yeah.
one version behind
Okay.
um, of that, which I just thought was kind of a funny comment. They didn't want to be on the most recent one; they wanted to stay one behind, so the
Mm.
bugs got fixed. But
Yeah, but then they're
um,
missing out on the bugs that have been fixed.
that's true. That's true.
That's so
There's
my
trade-offs, huh?
recommendation is keep the old one, put on the new one, and and you've always got the fallback if you think.
Yeah.
But
Yep.
also, if you're if you're somebody who wants to drive your discipline, you can then feed back on that current release. And by the next release, there might be a model in it that's going to make your problem work
Yeah.
when it doesn't now because the software doesn't have the capability.
Yeah.
So
That flips the script
we
on it, huh?
listen very carefully here at Leap to
Yeah.
our clients and have meetings and push really hard to get them features
Yeah.
that we know will impact their problem, and to sell that to Ansys that
Yeah.
it's not just Joe that needs this, it's all these other customers, and
Yeah.
it works because we have a good track record at doing this, and track record sells.
Yeah. That's a great point.
Well,
Get in the driver's seat and help steer what features you want, right? Instead of just
absolutely,
reacting. Yeah.
it's so important to do that because there's an infinity of choices of what you could spend your money on in a future release of software, and
Mhm.
and companies are going to do that to try and optimize, obviously, their sales, their customer satisfaction, their long-term goals. But there's certainly always time in it for making sure that um, the usability improves, the missing term in a combustion model that would allow you to do X or Y gets added so that users can do that.
Yeah.
Mhm.
Yeah, that's great insight. So, continuing on with CFD and the paper that you wrote, I believe one of the things you also talk about is that CFD still has a very big role to play in the industrial revolution we're having,
Mm.
right? This digital transformation, digital
Yeah.
twins. We see a lot of this. And one of the things that I don't know that I said yet, but you're based in Australia, and my understanding of the market in Australia is there's a lot of mining
Mm.
and the process industry there is very um, that just plays a huge role of the economy of where you're at and the type of work that you see. I just want to bring that to the attention
Yeah,
as we ask this
that's
question.
correct. Yeah.
And so compared to maybe some of your legacy, and I call legacy because they were maybe some of the earliest ones to
Mm.
adopt CFD, is your aerospace, external aero, your automotive stuff. And so
Mm.
my observation is that when it comes to multi-phase flows, there is still so much more that is yet to come in
Mm.
terms of model fidelity. They're doubly difficult when you talk about getting lab data for
Mm.
multi-phase flows or experimental data, because
Mm.
how do you even measure some of the things we're trying to measure? And
Mm.
not that these problems don't exist in those other domains. I'm just saying it's a nuance that
Mm.
maybe is a little bit more layered when we talk multi-phase flows,
Yeah.
process industries.
Mm.
So now that we've set the stage for that, part of the article you wrote was this gap, right? We're seeing students come out of university without mathematics. They're not as well prepared as they need to be for the problems that are being demanded we solve
Mm.
in
Mm.
industry. And so
Mm.
what what are those gaps that you're seeing in particular as we look going forward of what skills students, professionals need?
Mm.
And yeah, what do you think those gaps are that we're seeing?
Yeah, I think there's a lot of specialist areas, like you've just said, multi-phase flow, where it requires a lot of learning. Just understanding the equations, the fact that it's a mixture of rigorous balances and empirical correlations, and the empirical correlations always have boundaries, um, and you mustn't push them outside of that. Or if you do, you need to be super clear in your mind that you have, um, and that there's lots of physics going on that may or may not be important. And one of the curses I see is that people tick every button, right? So in multi-phase, you can have drag, lift, added mass, pressure force, thermophoric force, and people tick that. And then you say to them, but, your temperature range is 5 degrees. How can you possibly need a thermophoric force? Oh, but it doesn't do any harm to tick it on. And I always say to them, it does. The harm it does is to show that you haven't got a clue what you're doing. Yeah. And I think, see, that's important because if you're working with other people and the engineers know these things, they'll think, well, my goodness, those guys don't have a clue what they're doing. They're just box tickers. I've recently had a big argument with somebody about a paper they've published, which is absolute garbage. And they go on and on about lift forces being important, and they've got 1 micron air bubbles. And I've said to them, lift requires drag and vorticity, or slip velocity and vorticity. These things are moving at so low slip velocity, it doesn't matter what the vorticity is, you're multiplying it by 0. Just do a hand calc. And that's the other thing. They're not capable of doing a hand calc today. They're not willing of making an approximation. And you'll see them doing it. And they'll be looking up what the density of water is, and they'll be putting down 6 digits when you say, and I'll be doing it, and I've written 1,000. And they're like, oh, but it's cold water. It's more like 998. And you're like, they didn't use a slide rule. Okay. That is a big, big issue with this. They did not use a slide rule. So they want infinite precision when we knew that 1 or 2 digits was superb, but it got you the right log of the answer. And so it's so important with these physics to do those hand counts. And
Yeah.
I always want to do that up front. Now, what I've done for my own personal use is I've got a little Python file where I don't like spreadsheets because I find them a horrible, disgusting thing. But I can stick in, a velocity, a length scale, a viscosity, and it will churn out a certain set of numbers for me. And I've
Yeah.
got them there to have a bit of a look at and to make
Yeah.
clear in my mind what I'm doing and why. And so you can use this, you can add to it. But when you start having a conversation with people, and one of the big things is that loads of engineers talk about laminar flow. What they mean by laminar flow is smooth flow. Okay. They don't mean laminar as Reynolds number is low. They mean a smooth, undisturbed flow. And medics are particularly bad at this when you work at biomedical. Oh, we've got a nice laminar flow through there. But actually the Reynolds number is 5,000, and it's terminology. So if you can up front, when you sit down and start these things, have a feel for what's important, then it's much easier. I mean, I like to know what the settling velocity of a particle is when I'm doing anything with solids, because that immediately gives you a time scale.
Mm.
You know, I've got my 1 meter vessel, I've got a settling velocity. It's going to take 5 minutes to get to the bottom of the vessel. There's no point in running simulations at a transient for 2 minutes and thinking I've learned something.
Yeah.
And it's that knowledge of the physics as well that I think is important. I was super lucky. My first career move was I was sponsored by the UK Atomic Energy Authority and worked on steam explosions. This
Mm-hmm.
and we wrote our own codes for that.
Mm.
And you had to justify what you were doing. And so up front you made all these estimates
Mm.
and you justified the assumptions. And I think you should be doing that any single problem you do. It
Yeah.
doesn't have to be so rigorous, but the more detailed the physics, the more complex the physics, the more important it is to do this.
Yeah.
You know, multi-phase combustion are two that spring straight to mind. If you don't have a good understanding of what's controlling the combustion, then how can you pick a suitable model? And gaining that knowledge is hard. I mean, there are good specialist online courses maybe that you can self-pace with. There are good mentoring from people who have got experience. And I would say that I work with a lot of companies that use me as a mentor. The ones that are successful want outside input. They wanna pick up things more quickly than just trudging through it, having to learn by their mistakes, shall I say even. So you've got to have specialists involved if you're using specialist models.
Yeah.
And you know, you're lucky because I've worked with so many people now that I've been able to understand their insight. And you have somebody like Florian Mentor who you've spent time with, and you just know you can start thinking like he thinks when you approach a problem because he's spent the time to show you how he thinks through what he's doing. And it was I had a great privilege of knowing Phil Stopford before he passed away on combustion. And I learned so much because he had this superb approach to being able to look at what was important, explain it to you, and do a test case before we jumped into a furnace. We were always burning coal in a duct because we wanted to be sure that what we put in for the coal properties and the heat release and that were going to come out correct. We can't do that in a full-scale furnace. It's too complex, you know?
Okay.
And so
Yeah.
all of these things that help you understand the physics and that mean you don't mess up at the large scale. You build. And I think, you know, as we try and do more and more complex things, as we try and move away from just bubbles and droplets in multi-phase, but have regime maps, you have like the top flow type models where you can have different regimes happening. You need to know what those are and what their characteristics are, because you can see whether your results look physical then, you know. And I still read books. I still have a lot of books on my bookcase, as you can see. And I get them out and use them.
Yeah.
I do use the internet, but there's no substitute for a good book. Anybody doing this should have a copy of Bird, Stewart, and Lightfoot Transport Phenomena on their desk. And I'm sure, yeah.
I'm so happy. This is the most recent edition. I
Mm,
just bought it maybe a month ago.
mm.
Anyway, I've heard it recommended so many times.
It's, you know, and if you follow the ideas in that and the way they build things up, that'll take you through to the most complex physics you ever need to work on.
Yeah. Well,
Mm,
I was laughing throughout that early on. My dad used a slide rule
mm,
at university,
mm,
and he gave it to me. Um, and anyway, when you were starting, I just thought I had a professor that used 9.806 instead of 9.81.
mm, mm.
And it just reminded me of, anyway, it was just very humorous as you were
Yeah.
talking about early on of the numbers and recognizing I've titled many presentations I've given in industry, How Close is Close Enough?
Mm,
Because some engineers, and it's There's a scientist in each of us that really
Mm,
wants to be as precise as we can, but when it really comes down to it,
yeah.
um, often close enough is is rounding to 1,000, like you said,
Yeah.
or even bigger than that. So depending on what we're working on. So
And we have to think what we
excellent.
can measure.
Yeah.
How well can we measure something? Because any good experimentalist doesn't give you a number, they give you error bars. And we've got error bars too in what we're
Yep.
doing. It's
Yep.
maybe harder to quantify them, but sometimes it's not. You can run a couple of cases with different turbulence models, and are they broadly the same or are they totally different? And if they're
Yeah.
totally different, then you know that there's some important physics that changed
Yeah.
between the two. Um, yeah.
Yeah. So I find this a bit of an irony, right? At the very moment when we need people with a deeper understanding of the fundamentals and
Mm,
a deeper understanding of being able to clearly attack and approach a problem,
mm,
it feels like there's a lot of external forces making that even more difficult
mm,
to get those people. And if you want to be one of those people, to know how to do that and to choose
mm.
to become one of those people,
Right.
right? That and so it's this irony. So again, coming back to this training idea, simulation training for industry, and you mentioned this in your paper, is more important now than ever.
Mm,
And so, do you have any thoughts? You sit on, as we've talked about, you have one foot in academia, a foot in industry.
mm,
Who do you think is best suited to meet that need? And perhaps it's not one; it's a combination of both. Do we need more industry short courses? Do we need more a different approach in our academic courses that we're offering, or
mm.
what do you feel like is going to help us meet that need?
Yeah. Look, I from the academic side, you see the pressure that the disciplines are getting wider. There's more
Mm-hmm.
and more, chemical engineering now is also biochemistry and that. There were not
Mm-hmm.
necessarily those disciplines 30 years ago. So students have got a lot more options.
Yeah.
There's a lot more management type content, the soft skills, which again, if you see how some students present now their fourth year thesis, it's better than what 40 or 50-year-olds present at an international conference because they've got the skills. They can actually make decent slides and have the confidence to speak. So there's
Yeah.
super advancements there. But that's meant that you've had to peel back a lot of the more fundamental
Mm-hmm.
mathematics. There's also the change in what education is.
Mm-hmm.
So education was about providing an educated population with a certain set of skills that the country needed. It needs engineers because we don't make anything without engineers. But now it's much more important to be catering for your offshore um, students, numbers. So
Mm-hmm.
governments haven't necessarily invested in the engineering disciplines and that. So universities have to make that up with overseas students. And what's the golden rule of taking people into a course? They must come out of it, and so that means you can't enforce very high standards of mathematics. I
Yeah.
have a very close collaboration with the University of Toulouse in France, and they haven't gone down this route. They still have in France what's called preparation, where you do science and mathematics for multiple years, and then you do the engineering topics. So they've got these fundamentals, and having students to co-supervise students that have gone through that process, you notice that they're much more willing to engage with the mathematics.
Yeah.
I personally would turn the clock back. I would start bringing more mathematics into the course and integrating it. And I think when you talk um, transport phenomenon, that was a great time to integrate mathematics and start
Mm.
showing the beauty of it because, I get people laughing at me, but I tell them that certain equations are beautiful and there's so much you can get from them. And you don't need to know much more than their structure to rule out all sorts of things,
Yeah.
and to understand what boundary conditions make sense. I've got
Yeah.
shockwave, supersonic flow. Well, you know, you can, it can the shock wave doesn't know what's ahead of it. It's going so fast, it doesn't see the exit coming. And trying to explain that from things like characteristics and that, it's just so natural to somebody who's been brought up with a really good PDE course. And I think of all the foundational things I did in a maths degree, understanding the structure of partial differential equations was one of the keys, because it tells you about the physics. It also tells you about what sort of things you can approximate and how to do it. And somehow we need to get that back. I really believe that. It's very hard because you might say, okay, let's move to a system where, the first year of a PhD is doing courses. And I know in America, that's a very strong effect. But that's combined here with the fact that, 3 years is the 3-line whip. 3.5 years and you'll get away with it. 4 years and you've got a flogging. It's so important to keep graduating. So they don't have time to incorporate those things.
Yeah.
But I think it's needed. It really is, because we mentioned earlier Industry 4.0, and that's where the simulation on its own is not the end goal. You've got to take it beyond that into predictive models, into simplified results that can be put into control systems and that, but without losing their fidelity, and understanding how you go about those things and how you would choose the level of your CFD model such that you could run 1,000 cases and use an optimizer to produce a model prediction that will then run in literally seconds on a control system. And that is, I just can't even conceive of the ideas without having good mathematics.
Yeah.
And when we talked about the complex physics, one of the really key things that's changing is that people think on a multi-scale now. Yeah. So you've got to think on multiple scales of both space and time. And how do you integrate those into a good model? And of course, you have to approximate to do that, but you have to understand what you can approximate. How can you run a CFD simulation that's doing erosion of a pipe, where erosion occurs over a year, when the individual impacts with the wall take less than a millisecond? And that's the sort of scale problems that people now have answers to by doing clever things and scaling and projection and that. So it's really, really hard. I don't know how. See, I can't put myself in a position of somebody who's trying to do this without mathematics. So I don't know how their mind is working. But it must be super hard.
Well, it's so interesting. I was reading a book recently. It's called The 5 Equations That Changed the World. And the author is a mathematician, I believe. I can put the link in the notes as well. But one of the things that they talk about in the introduction to the book, so it's about Newton, Faraday, Bernoulli, Einstein, and the thermo guy, Clausius. Anyway, so at the beginning, he talks about how for years there have been multiple attempts. I think it started in like the 1700s to have a universal language. And his argument is that mathematics is the closest thing we have to a universal language. And he goes on to talk about the beauty of equations, because they're so succinct and concise in the brevity, but what they communicate is so broad and deep. And so that really just struck me as you were talking, that you said you get maybe some people laughing as you talk about the beauty of equations, but there is a beauty to it in the clarity and the succinctness, the conciseness of what it means across so many different scales, and what matters, what doesn't, because you can look at it. So I really, I really agree with that. And the older I get, the more I find myself diving deeper into the math,
Mm,
which I think is an irony. I did not have as rigorous, or let me back up. I did not exert as much effort as I could have to go
mm,
deep on the mathematics, but I find
mm,
myself paying for it now and wanting to go deeper and deeper
mm,
into the
mm.
math. So,
It's a tool
um,
that never lets you down.
yeah, yeah, it's
Yeah,
certainly a tool that, when used well, will put you mind. It's something that can make one decision instead of 1,000 small decisions, right? You
yeah,
could use
yeah.
other methods to make them.
Absolutely, absolutely.
So there's one statement, and this is the statement when I first read it. I was going through. Um, this is from your paper. This is what you say. You say, there are relatively few people with extensive and wide skills who can assist with implementation of a CFD strategy into a company.
Mm,
If you find one, keep them.
mm,
And we've been answering this question
mm.
implicitly all throughout our
Yeah,
discussion today,
yeah,
right?
we
And
have.
most notably, you gave the example of Gary, right?
Mm,
And at Alcoa, and he'd kind of done this for them. He was their first guy, got him
yeah,
some quick wins, got
mm.
him there, and then he's continued to grow on that. But if you were to summarize, maybe in a list, what you feel like the most important skills are, or maybe just pull some things together for us, what do you
Mm.
feel like would be on that list of skills? We know mathematics would be there.
We
I
know
know
that.
enough about you now to say
Yeah,
mathematics is on
mathematics.
this list. There's no list that David makes for CFD that mathematics won't be
It's
on.
not on. So I think it's really important you know about the process you're going to model. Okay,
Ah,
so or if it's in a say domestic product scenario, know what that product does and what the key physics or chemistry in it is. So
mm,
so you've got to know how it works to some extent, because you can't apply your mathematics until you know how it works. Yeah, because the
yeah.
mathematics sits there
What
in
is the mathematics?
isolation, unrelated to anything until you start drawing links to it. You've also got to be good at knowing what are the key issues that this company or this CFD simulations need to resolve. Um, are they practical? You know, up front, sometimes you say no. I need to know the external temperature of my cooktop to within zero point 0.1 of a degree. Can't, don't start, because there'll be so many assumptions about whether the wind's blowing or not, or the fan's on, that you can't do it. So you've got to have practical end
Yeah.
goals, if you like, and
Yeah.
don't start a simulation if you don't think they're practical. You've got to know how much time is available to do
Mm,
this. We're going to manufacture on Friday. Can you help us design a new rotor blade? No. And, it's really important to have that link. Um, it's really good it's really important to be a good communicator. And I guess that now is across the board, but being able to take your skills and communicate them to somebody else in their language. So it's no good me going and saying, about Reynolds numbers and Stokes numbers and that to somebody who is trying to settle some water in a water treatment plant, and they're not settling their stuff out. They don't care about numbers. What they care about is understanding, well, what's going wrong with our settler? Have we got a really bad flow in here? Have we done something that's stirring the settled bed up? And so you have to be on their wavelength too, understanding, what's changed. Listen to their experience. I think that
yeah.
you've got to be a good listener if you're going to work with industry, because they may not be able to articulate things in the way you need to know them. But as you listen, you start to get an idea. Oh, when did this happen? Well, actually, we had to change the pump, and the pump's about 20% more capacity now. Oh, and that's not CFD, that's not equations. That's listening to the end user and suddenly thinking, oh, I could do a simulation where I run with pump X, so now I'll run with pump 1.2X flow rate. oh,
Hmm.
look at the difference, you know, and
Wow.
that that link of communication, that ability to approximate, to do something quick and dirty. Um, and people call them agricultural simulations, where that some of the smartest people, smartest engineers are farmers. They have to repair. They have to get some. They can't not cut the harvest because their harvest is broken. They have to fix it up and get it going. And so, you need to do the same. You haven't got the perfect model. Can you get a flow field or something which will help the end user in your business make progress? And then you can always go back and refine. You can go to them afterwards and say, look, we solved your problem, but next time we might not be so lucky. So how about we do a bit of joint work to validate a model and understand what the capabilities are? And that person who's received the benefit from you is straight away going to want to work with you, because
Yeah.
they know that next time they have a problem, you'll have a better toolkit and you owe them. It's a mutual thing. So you'll
Yeah.
you'll actually help them out, and then they're going to help you out. And
Yeah.
so that integration is so, so important.
Yeah, there's a book that I read as a teenager. It was The Seven Habits of Highly Effective
Mm,
People, but it was an edition written for teenagers. But that's one of the things that has always stood out to me about this mindset of think win-win. That's one
yeah,
of the
yeah,
habits is think win-win.
yeah,
And when it comes to simulation, you touched on it earlier in the discussion that neither can succeed without the other.
yeah.
And that's not the way it's designed to be. It's designed. We're not asking everyone to be a mathematical expert, right? We can't
No.
expect someone whose day job is something completely different, ops,
Mm,
maintenance, to be a mathematical expert
no.
on that level. And so I just love as you're talking that it's this idea of, and perhaps even within a team, that you don't
Mm,
have to have one person who does all of these things perfectly,
no.
but throughout your team, getting the right team in place that
Yeah,
can deliver all these skills
yeah.
to the group, to the people. That's what we're going for.
Mm,
And maybe the first guy does have to have enough, or first girl does have to have
mm,
enough to be able to kind of punch through to prove
yeah.
we can do this. But yeah, I'm just trying to still keep the expectation high of what we need for the industry and what's coming,
Mm,
but still help it. I don't want people to feel overwhelmed, right? We're not asking
no.
anyone to be superhuman. We're just
No.
saying this is what it's going to require, and these are excellent examples that you've
Yeah,
provided.
that
So
I think, that whole thing of just being a good colleague with people who are not in your discipline
yeah,
is the starting point, and you learn so much. So I absolutely love when I go to visit simulation people who've got our software,
hmm,
where they say, "Do you want me to show you through the plant first?" Absolutely, because
yes, let's do
all
it.
of a sudden you can see the scale. You can see the difficult materials maybe that they have to work with, the end precision of what they want, and this is an air conditioning duct. It looks pretty agricultural, but that's the level they need to get the simulations done for. And then you go to
Yeah,
another place and they're showing you a satellite launcher that they're making. And we've got liquid oxygen here, so we have to be a bit careful. And so to me, that's been one of the most amazing parts of my job, is the number of customers I've been around their plant and learned about and seen
yeah,
real equipment. You don't understand what a turbine blade is until you've actually seen one. You
yeah,
see all these drawings in books and photos, but when you actually
yeah,
see the hardware yourself, and the polish on the blades and the angles, it's much more real than any photo you can ever see.
yeah. I had a professor so I was a civil engineering undergrad, and he was
Mm,
my geotechnical engineering professor. And he said, anytime you see a hole in the ground, go look at it.
yeah.
It'll benefit your career in more ways than one. And figuratively, I've tried to apply that to other
Mm,
areas, right? Not just
right.
geotechnical engineering. Obviously, I don't do that as a profession, but it was just exactly what you described, right? You're
Mm,
going to learn so much from paying
yeah.
attention
Yeah.
to the end users and the
Yeah.
problems that are being
Yeah.
solved. So to uh to kind of wrap things up here, what gets you excited about the future of CFD. We've spent a lot of time talking
Mm.
about the needs and maybe the gaps and how we can help, but
Mm.
I really want to end on what gets you excited? There's so much happening
Yeah,
that there's a lot to be excited about, I feel like is
a
where we
massive amount to be excited about, I think.
yeah.
GPU simulation. It brings to us the possibility of doing transient simulation so much faster and therefore having much more, much better, greater fidelity. I'm a complete convert to Gale resolving turbulence simulations because there are so many simple flows where RANS just doesn't cut it. Even with tunable models like Gecko, you cannot do it. You don't get the right answers. Whereas you jump in with SBS and you get it right. And the fact that you can do that so much faster now on GPUs means you can tackle bigger problems, you can tackle more physics. And I think with that comes the fact that as more people use these more complex models, development of the models that require a good turbulence input is actually more worthwhile
Hmm.
because there's no point in having a great combustion model if really you can't afford to solve it. Yeah.
Yeah.
It's
Yeah.
so, the fidelity of these things is going up. The ability to co-simulate with that, I mean, CFD is only one of your skills. I mean, I do a lot of work where you're coupling it to structures because of fluid structure interaction. Got clients coupling it with very detailed electromagnetic simulations for, say, magnetic particle separation and that. So the fact now that you can couple things, there's a really nice trend as well I like, which is everything is going towards Python. So you're not having to mech around with multiple languages. You can use one, and therefore the people you work with, you can tell them learn Python, and that'll do
Yeah.
your scripting. That'll be what you lose as the structure for your expressions, for your user-defined functions, and so it's worth them investing in Python.
Hmm.
So as you look forward, it's like there's this whole area of flows that I've only been able to do approximately, and okay, approximately has got some benefit, but now we can do the better. We can get even more benefit, and we can start looking at some of the cases or problems for companies that weren't practical before
Hmm.
because RANS was giving you, okay, it was giving you like trends, but you could never match experiments well. But now
Yeah.
you can. And if you're interested in this, there's a whole series of papers I did with Gary at Alcoa. It's Gary's PhD,
Okay.
where we've shown the step change in what you can predict by going to SBS. Um, and I think,
And can you define SBS? I don't think I've heard.
okay, so SBS is a blended model that's in ANSYS where
Okay.
you decide that you're going to use the optimal model for each region. So
Okay.
when you're close to a wall, RANS equations are super good at boundary layers and
Yeah.
separating and that. But when you're away from the wall, you want to be using large eddy simulation.
Okay.
So SBS has a very sharp blend between using RANs at walls and
Okay.
LES in the bulk. So it removes the defects of both models. RANs is terrible in unsteady flow in the bulk, but LES is destroyed by ill use, where people claim they're doing full LES, but they haven't actually got a grid that will resolve it near the wall, and they've hacked on a log wall function, but then their flows are semi-transitional, and so they're forcing a log layer and that. Whereas if you hook it onto something like SST has this nice fallback. It'll drop down to laminar flow. And so those hybrid models, it's like detached eddy simulation, only a light year better. Um, and so what it means is that you can have the resolution where you need it, and you can start predicting regions of intense turbulent mixing and get the scales right, which is so important if you're going to do things like high fidelity residence time calculations in a reactor, or even settling calculations in a where you've got particles, because you can now get the large scale flow field well, and the
Hmm.
particles take care of themselves through that.
Yeah.
Um,
Yeah.
so it's computation plus the physical models that's doing, and then to me as well, the ability to wrap all that stuff up and put it into a optimization package, which will let you either do optimization or more likely fit a model, which could then be used for um, fast control type applications.
Hmm.
I'm super interested in what you can do with surgeons.
Hmm.
I'm doing a lot of biomedical now,
Hmm.
and the challenge is to be able to, take patient data and then produce responses to that in a reasonable time.
Hmm.
And so with these better models, you can actually do better at taking geometry, simulating, doing co-simulation if necessary, like fluid structure, and
Yeah.
and getting results that are more useful to a surgeon.
Yeah.
Um, and really that's medicine 4.0. It's the same as in industry.
Industry.
Um, and it's also coming into the way medical products and or procedures and that are validated. The FDA and that has seen the power of simulation, and in some areas are looking to mandate the use of simulation for certain things. So
Hmm.
this is not weakening physical testing. It's supplementing it and pushing the physical testing to be in the areas where it's really, really needed, and not just the simple things that could be done by a simulation.
Yeah.
So, oh, yeah, I wish I had another 50 years ahead of me. Um, I really do, because I think it's been an exponential growth, but that exponent is going up pretty quickly still. Every
Yeah.
time I see a new release of software every 6 months, I mean, there's more in it than I've got time to try. It is the best time to be in simulation.
Yeah.
And
That's
if you are a young person watching this video, and you think, will I have fun and a great career and an exciting time doing this? The answer is yes. Um, I would recommend it to anybody. Will I have to work hard? Yes, because there's no substitute for knowledge. There is no day that I go to work and don't go home knowing something I didn't know before. It's even at 66, you are learning every day that you do a simulation, because you get thrown other people's simulations to look at, to debug, and you learn so much. And
yeah.
it's never a chore to go to work. I honestly feel super privileged that I've had such an exciting career, and the combination of academia with industry is a tough one to manage, but it's hugely rewarding. I have the most wonderful, I've had PhD students that are friends for life. And that bond, you see them develop. Some don't stay in simulation, but what you do know is that when they go into other areas, they know what it is and they appreciate what simulation is.
Yeah.
And others have stayed and become professors in their own right, and have done great things. And it's a real privilege to have mentored young people. I
Yeah.
think that, to me, that's been the greatest part of this is having that privilege of mentoring and seeing people grow. I think it's what every academic should be striving for, but it's not what most are striving for now. They're striving for large numbers of publications, getting on a fast track to a fellowship, and quality's gone out of the window. And, you know, please let's change the system and go back to where there was time to mentor students.
Yeah.
Because
Yeah.
my question is, who can I hand my business over to? I have this client list working for multiple people. I've got no one. When I give up, that role dies and all that knowledge goes in the ground with me. When there's so much of it that's not written down. And I think, that experience of how you do things is something you can train people with. You can't pass across every specific piece of knowledge, but you can pass across that approach.
Mhm.
And if you've got a sound approach, you can go read a book or a web page to learn a piece of physics. You can go and talk to somebody who's expert in it and listen and learn about it.
Yeah.
But you can't do that without the right approach.
Yeah.
Mm.
Well, it has been evident from our discussion today how much you do care and want to mentor. And thank you for
Mm.
joining to share your knowledge, your understanding, your perspectives. And I know I have been edified and improved by listening. So thank you so much, David, for joining
Uh,
today. And really appreciate you sharing your wisdom and things you've learned.
Been an absolute pleasure. To me, it's a privilege to share, and maybe we could do other topics down the line.
Yes, I would love to. I'd love that.
Mm. I would love
So
to too.
we'll have
Yep.
to get round 2 scheduled. So,
Yep.
okay,
Definitely. Yep.
sounds good. Thank you. Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.